Hi everyone. Okay. Good morning. Is the audio clear? Am I audible? Okay. So let's start. So some topics were remaining in group theory. So let's cover all of those topics. So let's start quickly. We have already seen what is a group. What is a group? Group is nothing but we have a set. So this G is our base set. Okay. So this is our set of elements, and on this set of elements we define an operation. So this is the operation that we have defined on this set. So this G is the set of elements that we have. So this is the algebraic structure, and for this algebraic structure, if we satisfy four properties, and what are those four properties? The first property was closure property, then we have associative property, then we have identity property, identity element, and then we have inverse property. So if these four properties are satisfied, then what we will say? We will say that this algebraic structure is group. Okay, if these four properties are satisfied, all these things we have already seen. Let's see some additional things now. So what do we mean by order of a group? So this is the first thing that we will see today. What do we mean by order of a group? So order of a group is nothing but number of elements in that group. For example, you can take example. Let's assume you have this group. This group we have already seen in the last class also, true comma false, and our operation was, let's assume our operation is conjunction. So this type of group we have. Actually, first we will have to check whether this is a group or not. So let's not take this example. We can take some other example. For example, you can take okay, let me take, you take this example we are going to use again and again. So let me first cover this example. Consider this. We are going to use something called z of m comma addition. Okay, where m is some positive integer, So let's see whether this algebraic structure, what is zm? Zm is nothing but set of set 0, 1, 2 and so on till m minus 1. This is our zm. Okay, now let's see whether this is a group or not. So what I am saying this. Let's take this example. Let's take z5 comma plus. Let's take this. What is this? Remember, what is this? This is nothing but this z5. What is z5? Z5 is nothing but 0, 1, 2, 3, 4. Because I told you what is zm. Zm is nothing but set 0, 1 till m minus 1. This is the set. We are denoting, we are representing this set with zm. This is the symbol we are using, zm. Zm means from 0 to m minus 1. So z5 will be this 0, 1, 2, 3, 4 comma plus. Now let's see whether this is this group, and the operation is actually, the operation is modulo plus. The operation is modulo plus. What is the operation? Operation is modulo plus. What do I mean by modulo plus? Modulo plus means this operation is basically when I take a modulo m b, then it will be nothing but a plus b mod m. So this is our modulo plus operation. Okay, for example, if I take 3 plus 4, for example, if I take 3, remember the operation is not addition, the operation is modulo addition. So this is the operation, modulo addition. Okay, now what is this operation? This operation is nothing but, for example, 3 modulo addition 4. This is equal to 3 plus 4 mod m. What is m here? M is equal to 5. So mod 5. This is nothing but 7 mod 5, and that is equal to 2. So you can see, remember, 3 modulo addition 4 is equal to 3, because this is our operation. Our operation is modulo addition. Modulo addition means first you add and then you find the remainder. Because we have already discussed this thing, that this mod is nothing but the remainder operation. Okay, so 3 modulo addition 4 is equal to 3 plus 4 mod 5, because our this 5 is our m. Okay, so this is the algebraic structure that we have. Now let's try to find. Okay, so I have so far I have only explained the structure that we have. This is the algebraic structure that we have. Now let's see whether this algebraic structure satisfies the 4 properties or not. Let's see the first property. Is it closed? So the closure property, yes, closure property is satisfied. Why? Because you can see if you take any two elements, then if you take any two elements from this set, then you know a plus b mod 5, you know this will give you remainder, because this is the mod is nothing but the remainder function. So this will give you the remainder, and you know that when you divide a number by 5, then what are the possible remainders? The possible remainder are 0, 1, 2, 3, 4. These are the possible remainders. So you can see that closure property is satisfied, because if you take any two elements from this set, and when you apply this operation, this modulo addition operation, when you apply, then you know that the result will also be present in this, inside this set, because of this mod 5. Mod 5 is nothing but the number that you will get when you divide by 5, because this mod is nothing but the remainder operation. So closure property is satisfied. Okay, now what is the next property? Next property is associative property. Associative property is also satisfied, because if you take any three elements, then basically this modulo addition actually behaves like addition, and we know that addition is associative. So you can just check this is also associative, because you do like this or you do like this, both are going to be same, because this modulo addition actually has similar behavior to addition operation. Okay, next, third property, that is identity property. This property is also satisfied. Why? Because this 0 is the identity element. You can check this 0 is the identity element, because when you add this 0 to any number, then you will get the same number. So okay, 0 is the identity element. And what is the inverse property? Inverse property is also satisfied, because every number has an inverse. See, 0 has the inverse 0. Okay, what is the inverse of 1? Let's check out what is the inverse of 1. Let me check it out. So I want to find the inverse of 1. So let's assume that inverse of 1 is b. Let's assume that inverse of 1 is b. Then what should happen? This should equal to 0, because 0 is the identity element. What is this? This is nothing but 1 plus b mod 5. This should be equal to 0. So what will be b? B will be equal to 4. You can see b will, because when you put b equal to 4, then the result will be 1 plus 4 mod 5 is equal to 0. So that's why you can say that 1 has the inverse of 1 is equal to 4. Inverse of 0 is equal to 0. You can just check it out. Inverse of 2 will be 3. Inverse of 3 will be 2. Inverse of 4 will be 1. So you can just check it out. Every element has inverse. Okay, so now you can say that all 4 properties are satisfied. Closure property, associative property, identity property, inverse property, all these properties are satisfied. So this is a group. This is a group. Okay, so remember this is a very standard algebraic structure. So let me just repeat this algebraic structure. This is nothing but Zm modulo addition. So remember, this is modulo addition. Okay, and this is Zm. What is Zm? So Zm is nothing but from 0 to m minus 1. Okay, this m is nothing but some positive integer. This m is positive integer. So this is your Zm is nothing but 0, 1 and so on, m minus 1. So this is your Zm. So this is your base set. Okay, this is your base set. For example, what will be Z4? Z4 will be 0, 1, 2, 3. This is your base set, Z4. Okay, now Khushbu, we have just started. I have taken one example and we are just looking at this first example. This is the first example we have taken. We are just checking whether this algebraic structure is a group or not. Okay, this is a very simple example we have taken. Okay, so Z4 is this is how we have defined Zm. Okay, now what is this operation? This operation is nothing but modulo addition. This operation is modulo addition. What do I mean by modulo addition? Modulo addition means modulo addition is like this. Modulo addition is like this. A modulo addition B is nothing but A plus B mod M. For example, if you have Z4, then what will be, for example, then what will be 4 modulo addition? What will be 2 modulo addition 3? What it will be? It will be 2 plus 3 mod. It will be 2 plus 3 mod, because this is 4 mod 4, and what will be the result? This is nothing but 5 mod 4. 5 mod 4 is equal to 1. So this is our modulo addition operation, and this is our base set. Okay, so this is a group. This algebraic structure is a group because this algebraic structure will satisfy all the 4 properties. Okay, so this is a group. Okay, now this is a very standard group, remember. So now let's see this group Z4 modulo addition. Let's see this group. Now in this group you can see this Z4 is nothing but 0 1 2 3. So what is the order of this group? Let's call it group G. Then what is the order of G? So this is how we denote order of G. Order of G. Remember, this is the representation. This is the mathematical representation of order of G. What is order of G? Order of G is nothing but number of elements in this base set. In this base set we have 4 elements. So our order of G will be 4 because number of elements in the base set is 4. So this is our order of this group. Okay. So for example, you can take another example. You can take, for example, set of integers under addition. This we have already seen. This is a group, set of integers, and this is addition operation. So this is a group, and for this group if you find order of Z, then order of Z is infinite. You can simply say that order is infinite. You can just simply say order is infinite. Okay, so we can take more examples. You can take this example. This is your base set and this is your addition operation. So this is, first of all, this is a group. You can check this is a group. Why? See, this is our base set. In the base set we only have 0, and this is our addition. First of all, this is a group. Why? Because closure property is satisfied. Why closure property is satisfied? Because you can see 0 plus 0 is equal to 0. So that's why basically when you take 2 elements 0 0, when you take 2 elements and then you apply this operation, then the result is also present inside this base set. So closure property is satisfied. You can just check associative property is satisfied because this addition operation satisfies the associative property. We know that addition is associative. And this identity property is satisfied because the identity element is 0. Okay, now the inverse property is also satisfied because 0 inverse is equal to 0. So you can see all these properties are satisfied. All these 4 properties are satisfied. So this is also a group. Okay, this is also a group. Let's call it group G. Then what is the order of this G? This is equal to 1 because number of elements is 1. Remember, in this base set we have only 1 element, so number of elements is 1, and this is our order. So order of G is equal to 1. So this is the first definition that we have seen, and this definition basically this is the definition of order. Now let's see the power of elements. Let's see power of elements. So let's take one example. Let's take this this set of integers and this addition operation. We have seen this is a, let's call this group G. We know that this group G is this algebraic structure is a group. We have already seen. So now for this, now let's define. So power of element. If you have any element A and you want to define the power of this a power n, if you want to define, then that is nothing but a star a and so on n times. For example, what will be a square? A square will be a star a. What will be a power 1? That will be a. Okay, what will be a power 3? That will be a star a star a. So this is how we define power of element. For example, if you have this group, let's assume this group you have, and the base set is set of integers, and our operation is addition. So for this group, let's see what will be 2 power 4. Let's see what will be 2 power 4. So 2 power 4 will be nothing but 2 star, and remember here our operation is plus, so this will be nothing but 2 plus 2 plus 2. So finally what will be the result? Result will be 8. So you can just check. So 2 power 4 will be equal to 8. Okay, here remember okay, of course, don't use your mathematics, don't use that mathematics that we have studied till our school. 2 power 4, okay, don't say that 2 power 4 is 16, okay, because this is how we define power. Okay, a square is equal to a star a, and remember here our star is plus. So what will be 2 square? 2 square will be 2 plus 2, so that will be 4. What will be 2 cube? That will be 2 plus 2 plus 2, that will be 6. Okay, so this is how we define power of element. And remember, power 0 is defined to be any element to the power 0. This is defined to be the identity element. Okay, so for example, in this group G, the identity element is 0. So if you want 2 power 0, then that will be 0. If you want 3 power 0, then that will be 0. If you take 0 power 0, then that will be 0. So remember, this is how we define power 0. So any element to the power 0, that is equal to identity element. Okay, so this is how we define power of element. Now you can see very easily, you can see if you have a power m plus n, then what it will be? It will be equal to a power m a power n. Okay, because because for example, a power 2 plus 3, what is this? This is nothing but a power 2 a power 3. Why? Because this is nothing but a power 5, and a power 5 is nothing but a star a star a star a. This is your a power 5. And what is this? This is a square a cube, that is nothing but a star a, and this a cube is nothing but a star a star a. So you can see this a power 2 plus 3 is equal to a square a cube. So this is okay, this you already know. Actually this is very similar to the operation that we do in mathematics, that we do in general mathematics. Okay, in general the school students also do this kind of thing. A power m plus n is equal to a power m a power n. So this is remember, of course, so this is your power. So this is how we can find power of element. Now let's see the negative power. We can also define negative power. So for example, if we want to find a power minus 2, then that is nothing but a power minus 1 whole square. So this is how we define negative power. So basically a power minus 2 is nothing but a inverse power 2. Okay, a inverse whole square, that is nothing but a inverse star a inverse. So this is how we define negative power. For example, if you want a inverse, then that is nothing but a inverse. For example, if you want a power minus 3, then that will be a inverse star a inverse star a inverse. This is how we define power, negative power. Let's take this example, z and plus, this same group we can take. So in this group, if I want to find what is 1 power minus 3, then what it will be? It will be nothing but 1 inverse power 3. What is 1 inverse? 1 inverse is nothing but minus 1. You can see inverse of 1 is nothing but minus 1. Minus 1 power 3. What is minus 1 power 3? That is nothing but minus 1 plus minus 1 plus minus 1. Okay, because remember our operation is plus, so that's why minus 1 plus minus 1 plus minus 1, and this will be minus 3. So 1 power minus 3 is equal to minus 3. Similarly, you can find, for example, what is 4 power minus 2? That will be equal to, very similarly you can find, this will be equal to 4 inverse power 2, and that is nothing but, what is 4 inverse? 4 inverse is nothing but minus 4 power 2, and this is nothing but minus 4 plus minus 4, minus 4 plus minus 4, this will be equal to minus 8. So this is how you can define negative powers, this is how you can define positive power, and this is how we can define order. So these three things we have seen. Let's move on and let's see the remaining concepts. And see, I gave you this group. If you remember, today I gave you this special group. I gave you this very cute group. I gave you 0 and addition. This very cute group, I gave you just one element in this. So this is a group we have just seen. Okay, just 5 minutes ago we have seen that this is a group. because it satisfies all the four properties. Actually this is because this only has, you can see this, in this group we only have identity element, because for this group the identity element is 0. So in this group, in this base set, we only have identity element. Okay, there is nothing other than identity element. The only element is identity element. So this type of group is called trivial group. What is this? This is called trivial group. Okay, because of course, see, if I ask you to make a group, let's assume you know the definition of group, and if I ask you to make a group, then the one thing you already know, that in any group the four properties must be satisfied, and the third property is identity property, means every group must have identity element. Okay, so if I ask you to make a group, then the very basic group that you can make is this. Just take identity element. This is the very basic group that you can make. Okay, what I am saying this, that every group must have identity element. Okay, because in the definition of group we have seen this thing, that in the definition of group we have seen that the third property is identity property, means identity element must exist. Okay, so if I ask you to make a group, then the very basic group that you can make is like this. Just put identity element. Okay, because you can see all properties will be satisfied. Why all properties will be satisfied? Closure property will be satisfied. Why? Because E star E will be equal to E, because E is the identity element, so E star E will be equal to E. And associative property will be satisfied, because of course all these things will be satisfied. Associative property will be satisfied because there is only one element, so associative property will be satisfied. Okay, closure property, okay, identity property, inverse property, every property will be satisfied. So this is the very basic group you can make. Okay, so this is called trivial group. Basically trivial group is a group in which the base set only has identity element. Remember this thing, the base set only has identity element. So this is the trivial group. Let me ask you one question. So this is my question. Is every order one group, is every order one algebraic structure? Is every order one algebraic structure a trivial group? My question is every order one algebraic structure, this is algebraic structure, a trivial group? You can just actually check. The answer is no. Why? Take this. Now this, okay, you can just check this. This is not even closed. The closure property is not even satisfied. Okay, so that's why you can say the closure property is not satisfied. This is not a group itself. Okay, this is not at all a group. Okay, so that's why remember when we define trivial group, remember this thing. When I define what is a trivial group, then trivial group is a group. First of all, it must be a group. Group of order 1, because first of all it must be a group, so if it is a group, then it must have identity element. So, and because it is order 1, then basically you only have identity element. So this type of group is called trivial group. So remember, this is the trivial group. This is the definition of trivial group. Very easy. Just put the identity element, because every group must have identity element. So what you do, just put the identity element. This is the very basic group you can make without any headache. This is the very basic group you can make. Okay, so let's see the next concept. The next concept is, what is a subgroup? Let's see what is a subgroup. Subgroup means, first of all, subset plus group. Actually this subgroup you can remember this like this. Subgroup means, sub means subset, and group means group. So subgroup is nothing but a subset and a group. So basically, for example, let's assume you have a group G. Then H is subset, H is subgroup of G if and only if H is a subset of G and H is a group. This is the definition of subgroup. What is subgroup? See, remember, subgroup is nothing but subset plus group. So if you have a group G, let's assume, then H is subgroup of G if and only if H is subset and H is a group. So these things must satisfy. Then you will say that it is a subgroup. So how do we denote it? We denote like this: H is a subgroup of G. This is how we denote. This is H is a subgroup of G. This is how we will read it. Don't read it like this: H is less than equal to G. No, do not read like this. This is a mathematical notation, okay, and basically this notation we use to denote subgroup. So when we say H is subgroup of G, then we denote like this: H is subgroup of G. Okay, let's take example. Let's take example. So for example, this Z comma plus. Now this. So this is our group. So let's call it G. So this G is our group. Okay. And let me ask you a few questions. The question one. So H, I am defining H1. What is H1? H1 is nothing but 0, comma plus. First of all, is H1 subgroup? So my question is H1 subgroup of G? This is my question. Try this. So you can see, yes, this is true. You can see this is true. Why? We have just seen, just 5 minutes ago, we have seen that this is a group. First of all, H1 is a group. You can see, first of all, H1 is a group. Okay, we have just seen, because this 0 is the identity element. So this is the trivial group actually. This H1 is the trivial group. So first of all, this is a group, and also this is a subset. You can see this is a subset because 0, this is a subset of Z. So subset and group, both properties are satisfied, subset and group. So we can say yes, it is a group. Okay, actually every trivial group is a you can have any group. Let's assume G is your group. Then trivial group is always subset of subgroup of G. This is how you can see. Let's take more example. So this is your group G, this is your group G, and my next question is, I am defining a new group. Okay, I am defining a new group H2. Let's see this. Now my question is H2 a subgroup of G? This is my question. You can see the answer will be no, because we have just seen, just 5 minutes ago we have seen that this is not a group. This is not even a group. This is a subset, but this is not a group. See, remember, this is subset. Yes, subset it is. This is a subset, but this is not a group. This is not a group. So we can say that this H2 is not a subgroup. Okay, let's see next question, S3. What is S3? S3 is ZE, means set of even integers. Set of even integers. Did you remember ZE? ZE means set of even integers. Okay, and plus. Let's. And my question is S3 a subgroup of G? This is my question. Is H3 subgroup of G? So you can check, yes, this is true. You can just check, this is true. So you can check this is true. Why? First of all, this is ZE. ZE means set of even integers. So this is subset. First of all, this is a subset. Okay, and also this is a group. This is a group. Why? Because the closure property is satisfied. First of all, even plus even is equal to even. So closure property is satisfied. Associative property is satisfied because addition is associative, and identity element is 0 because 0 is even integer. So identity element is 0, and the inverse property is also satisfied because the inverse of 2 is -2. The inverse of 4 is -4, and so on. So this is how you can say This is how you can say that this is a subgroup. Yes, so this is a subgroup. S3 is a subgroup of G. So this is how you can find whether a group is a subgroup of another group or not. So this is how you can very easily you can find. Okay, so let's see next concept. So this was the concept of subgroup. Okay, subgroup means subset plus group. Okay, so remember this thing. If you have any group, let's assume you have any group G, this G is your group, then two things are definitely true. G is a subgroup of G, because of course G is a subset of G, and also G is the group, so this G is a subgroup of G. And the second thing, trivial group. What is trivial group? This is our trivial group. Remember, this is our trivial group. This is our trivial group. So trivial group is a subgroup of G. So these two will definitely be there. Okay, so these two will be definitely there. Now what is a proper subgroup? What is a proper subgroup? Proper subgroup means proper subset plus group. Proper subset plus group. This is the definition of proper subgroup. Basically, proper subgroup is a subgroup of G such that H is not equal to G. This is called proper subgroup. Okay, so remember, this G is not a proper subgroup. Okay, this is the proper subgroup. Okay, this is the proper. So basically, proper subgroup means H is not equal to G. This is the proper subgroup. Okay, let's see what is the so what is the trivial subgroup? What is the trivial subgroup? Remember, trivial, I am not saying trivial group, I am saying trivial subgroup. So trivial subgroup means H is trivial subgroup of so I will say, okay, H is this H, basically this H is trivial subgroup. This H is trivial subgroup if H either is equal to trivial group or H is equal to G. So this is called trivial. Remember, because I told you, if you have any group G, then the trivial group also the G, these will definitely be the subgroup of G. This we have already seen. These are called trivial group. Why these are called trivial group? These are called trivial subgroup. Why we call them trivial subgroup? Because for every group these subgroup will be there. For every group these subgroup will be there. So we call them trivial subgroup. So what is a non-trivial subgroup? Now, okay, if you know the trivial subgroup, then what is a non-trivial subgroup? H is non-trivial subgroup. H is non-trivial subgroup of G if and only if H is subgroup of G. First of all, H must be subgroup of G, and H is not equal to G, and H is not equal to the trivial group. Trivial group, you already know what is trivial group. This is the trivial group that we have. So basically, this is our non-trivial subgroup. Non-trivial subgroup means a subgroup which is not equal to G, which is not equal to trivial group, because this G is a trivial subgroup, this trivial group is also trivial subgroup. So that's the definition of trivial subgroup. That's the definition of non-trivial subgroup. That's the definition of proper subgroup. Okay, proper subgroup means any subgroup except G itself. Okay, that is the proper subgroup. Now let's see the next concept, that is Kelly table. So this Kelly table, there was this mathematician, his name is Kelly. So on his name we call it Kelly table, but the other name for this table is group multiplication table. Group multiplication, or you can say group behavior table. Group multiplication table, or you can say group behavior table. Okay, so what is this Kelly table? This is actually nothing but a different representation. For example, if you remember, in relations, for the same relation we had many different representation. The same relation we could represent using graph, using arrow diagram, using set notation, okay, using matrix representation. So for the same thing you can have different representations. Okay, so that's this Kelly table is nothing but just a representation of the behavior of the group. Okay, let's take one example. Let's take one simple example we can take. So consider this group. This we have already seen this. So Okay, let's take this group. I'm going to give you a new group that we have not seen so far. This group, consider 1 minus 1 iota minus iota and multiplication. This is the group. Remember, what is this iota? This I is called iota. This is the word. This I is called iota. What is this iota? Iota is a complex number. This iota is a complex number, and this iota has this property that iota is equal to square root of minus 1. This iota is what? Iota is equal to square root of minus 1. Okay, so what is iota square? Iota square is equal to minus 1. From here you can see iota square is equal to minus 1. So this is iota is nothing but a complex number. Okay, so this iota is a complex number. Anyway, so yes, complex wala iota, yes. Okay, complex number wala, yes. Okay, so this is your 1 minus 1 iota minus iota, and this is multiplication. Now for this, first of all, this is a group. Okay, you can just check. I will leave it as a homework. You can check. The closure property will be satisfied. The associative property is satisfied because multiplication is associative, so associative property is satisfied. The identity element, what is the identity element? Identity element is 1. Okay, the identity element is 1 because for multiplication the identity element is 1. Okay, and the inverse property is also satisfied. What is the inverse of 1? Inverse of 1, first of all, inverse of 1 is equal to 1 because this one is the identity element. Okay, and remember, inverse of identity element is always identity element. Inverse of identity element is always identity element. Okay, so the inverse of 1 is equal to 1. The inverse of minus 1 is equal to the inverse of minus 1 is equal to minus 1. Actually, you can just check. Let's assume that inverse of minus 1 is b, then this should be equal to 1. Then what should I place in place of b? So inverse of minus 1 is minus 1. Inverse of I is nothing but minus I, and inverse of minus I is equal to I. You can check. Inverse of I, let's assume inverse of I is b, then I multiplied by b should be equal to 1. So what should I multiply with here? If I multiply with minus iota, then what it will be? It will be minus I square is equal to 1. And what is I square? I square is minus 1. So finally you will get 1. So that's why inverse of iota is equal to minus iota. Inverse of minus iota is equal to iota. Now, so you can see, first of all, this is a group. Okay, so first of all, this 1 minus 1 iota minus iota under multiplication. So this is the multiplication operation, and this is our base set. First of all, this is a group. You can just check, this is a group. Now we can represent this group with Kelly table. In this Kelly table, basically what we do in this Kelly table is similar to matrix representation. What we do here, we put the operation. So the operation is multiplication, so here we put the operation. Okay, this is just a convention, like, okay, this is just a convention. This is how this mathematician Kelly, he defined this Kelly table. Okay, so this is just a convention that we put this operation here, and then what we do, we put these elements here, 1 minus 1 iota minus iota. We start with identity element. Remember, we start with identity element. Okay, so this is how we put them. So in the same order, if you are putting like this, you can put like this. So this is how you can make the Kelly table. Okay, so now what will be the entries here? Very easily you can write down the entries of this Kelly table. What is this? This is nothing but 1 into 1. This is nothing but 1 into 1. So this, because see, this 1 is the identity element, so you multiply it with anything, you will get the same thing. Okay, because this 1 is the now what is the minus 1 into 1? That is also minus 1 iota minus iota, because this 1 is the identity element. So you can see, this is how you can fill the Kelly table. Now let's see, what is this? Minus 1 into minus 1, what it will be? It will be 1. Minus 1 into iota, it will be minus iota. Minus 1 into minus iota, it will be iota. Okay, so what it will be finally? Iota into minus 1, that will be minus iota. Iota into iota, that will be minus 1, because remember, iota square is equal to minus 1. So what will be iota into minus iota? That will be 1. And what will be minus iota into minus 1? That will be iota. this will be +1 and this will be -1. So this is your Kelly table. This is very easily you can find the Kelly table. So this is just a representation. Remember, this is just a representation. In your exam they might give you Kelly table. Okay, so remember, when they give you Kelly table, then basically what they are going to do, okay, they are okay, let me tell you. So these are just the elements. Okay, this is just the header. These are just the header. Okay, these are just the header. The main important part is this. Okay, this is the main important part. Okay, so this is just a header. This is just a header. Okay, this is just a header. Similarly, this is just a header. Okay, so the main important part is this inside thing, and this will tell you the behavior. This will tell you the behavior. Okay, so you can see, for example, you can from this Kelly table you can very easily find what is iota multiplied by iota. From this Kelly table you can find iota multiplied by iota is equal to -1. From this Kelly table you can very easily find. Okay, so this is how we use Kelly table. Okay, so let me give you another example. Let me give you Kelly table and then I am going to ask you questions. Okay, so this is our a b c. This is the so let's take only 2 elements we can take. Let's take 2 elements. Okay, so this now, and our operation is star. Okay, so tell me, is this, first of all, is this a group? This is our Kelly table. Now tell me, is this a group? Is this a group? This is my question. You can just check. Let me answer. This is not a group. This is not a group. Very easily you can check. This is not a group. Why? See, this is closed. It is closure property is satisfied. So the closure property is satisfied. You can see. Okay. But let's see associative property. Let's check associative property. Is associative property satisfied or not? Let's check. Let's check A star B star A. Let's check this. So if we do this, then A star B is equal to B. You can see A star B is equal to B. B star A is equal to A. So this will be our result. Let's check A star B star A. Let's check this. Then what is B star A? B star A is equal to A. What is A star A? A star A is equal to A. So anyway, actually don't go for associative property because it will take a lot of time if you check associative property. The best way is to check identity property. That is the best way. Okay, if you check for associative property, then you will have to check many things. Okay, you will have to check many combinations you will have to check. Okay, so don't go for associative property, go for identity property. Let's see whether there is identity element or not. Assume that A is the identity element. Assume that A is the identity element. Then what should happen? If A is the identity element, then B multiplied by A, that should be equal to B, right? If A is the identity element, then B multiplied by A should be equal to B. But you can see B multiplied by A is equal to A. So A is not identity element. Let's assume that B is the identity element. Let's assume B is the identity element. Then what should happen? If B is the identity element, then A star B should be equal to A. A star B should be equal to A, but A star B is equal to B. So that's why you can say B is also not an identity element. So in this table you can see identity element is not there. Okay, so this is how you can check. This is how you can very easily check whether a Kelly table is represents a group or not. Now let me give you one more example. Consider this. Is this a group? You can check. This is a group. This is actually your trivial group. You can see this is your trivial group. Okay, so in this group you can see there is only one element in this group, and this is your operation, and this is the trivial group because you can see E star E is equal to E. So this E is the identity element, and this is how you can. So this is your group. Okay, let me take another example. Tell me, is this a group? you can check this is a group. Yes, this is a group. Okay, this is a group, because you can see, first of all, is the identity element. First find what is identity element. Is the identity element, you can see. Why? Because this you can see this this is EA, this is EA, so E is the identity element. Okay, and so E is the identity element. Also you can find that this is closed, because you can see all entries are EAAE, so all entries are all results are basically inside, so this is closed also. Identity element is there, closed, it is closed also. You can see actually this is a group, this is associative also, and this is inverse also. You can just check it out. Okay, very easily you can check it out. This is associative, and this is this is inverse also. For example, what is the inverse of A? What is the inverse of A? Inverse of A is nothing but you can see inverse of A. So let's try to find what is inverse of A. Let's assume that inverse of let's try to find what is inverse of A. Then that should be equal to E. You can see. So just check what is happening. So inverse of A is equal to A. So inverse of A here is equal to A. So this is how you can see this is a group. Okay, it is associative, it is all these properties are satisfied. Okay, so now let's see the next question. So let's see the next yeah, some properties of Kelly table we can see. Some properties of Kelly table, for a group. For a group you can see some, if you have a group and for that group if you make a Kelly table, then some properties will be there. Okay, what are those properties? We can check. So first of all, you can see, if you have a Kelly table for a group, let's assume the group G is the group, and if for that group if you have a Kelly table, then the first property is that in every row and also in every column you will have identity element. What I can say? I can say every row, every column will have identity element. What is the reason? See, the reason is this: because G is a group. First of all, G is a group. So if you take any row, let's assume you take this row, okay, so in this row you will definitely have identity element. Why? Because G is a group, so in this G there must be A inverse, because that is the definition of group. In group we have inverse, so there must be A inverse. Now when you do A into A inverse, then what you will get? You will get identity element. So that is the reason you can say that in every row, in every column you will have identity element. In every row, in every column you will have identity element, because in group every element has an inverse. Okay, so that is how you can find. Okay, so that is how you can prove this. Very easily you can prove this. Let's see the next second property. The second property is that in every row, okay, this is an interesting property. In every row, also in every column, in every row and column, no duplicates will be there. No duplicates. So whatever row you take, okay, you can take any row, you can take any column, whatever you want. You can see no duplicates will be there. Means what I mean to say is like this. Okay, let's prove it. Very easily you can prove it. Let's assume that in this row you have duplicate. By duplicate I mean, let's assume here also you have X, here also you have X, and let's assume this is B, this is C, and this is A. So what you can see that A star B is equal to X. Also you can see that A star C is equal to X. Let's assume. So actually we want to prove that there are no duplicates, so we can prove it by contradiction. Very easily we can prove. Let's assume that there are duplicates. Let's assume that there are duplicates. Means X is here, means in this row you have duplicate. Okay, then what will happen? A star B will be equal to X, and this A star C will be equal to X. Now all you have to do is just see what you can do now. So here what you can do, here you can do A star So okay, we can so this will be a star b is equal to a star c, because this a star b is equal to x, a star c is equal to x, so you can say a star b is equal to a star c. Now just multiply this a inverse both sides, just multiply this a inverse, you multiply this a inverse in both side. Then because group is associative, so this will be a inverse a. What is a inverse a? That is equal to identity element into b is equal to, what is this a inverse a? This will be identity element is into c. So finally this is equal to b and this is equal to c. So b is equal to c, you can see b is equal to c. So you can see this is a contradiction, because of course in the Kelly table what we do, in the header we put all the elements, so of course these b and c are different. Okay, so this is a contradiction, hence we can say that there will be no duplicate. Did you get this point? It is a very easy point. Okay, I am saying that you take any row, in that row there will be no duplicates. Why there will be no duplicates? Because let's assume that there is duplicate. Let's assume that there is duplicate, means x is here, x is here. Let's assume duplicate is there. Then what will happen? Then see, a star b is equal to x, a star c is equal to x. Now because this is equal to x, this is equal to x, so you can do a star b equal to a star c. Now what you can do? You can multiply this with a inverse. Similarly you can multiply this with a inverse. Now because group is associative, so you can find that a inverse into a is equal to identity element. So this is how you can prove. So these are the properties of Kelly table. Okay, these are the properties of Kelly table that we can have. Okay, so now the Kelly table is over. Let's see the next thing. Let's see the next concept, that is Lagrange theorem. This is a very important, you can Lagrange's theorem. You can just star it. This is a very important theorem. What is this theorem saying? This is a very simple statement. Okay, we will not prove it, because if you want to prove it, then it will take a lot of time. Okay, from the crash course point of view, the proof is not required. You don't need to know the proof. Just you need to know the statement of this theorem. What is this theorem saying? This theorem is saying that, let's assume G is a finite group. Let's assume G is finite group, means order of G is basically finite. I can say order of G is finite, means finite group. Let's assume that G is finite group. Finite group means order of G is equal to order of G is finite. Okay, let's assume. Now if H is subgroup of G, then order of H will divide order of G. This is Lagrange theorem. Very easy. Okay, this is Lagrange theorem. So Sakshi is saying didn't get it. B equal to C, in table both are X. How it is proved then? Okay, let me just take it again. See, okay, in the Kelly table what we do? So Sakshi, in the Kelly table what we do? In the Kelly table, this is the header. Remember, this is just a header. This is just a header, and this is also just a header. Okay, in Kelly table what we do? We put all the elements. Okay, of course we don't put same element two times. Okay, we put all the elements. For example, we put identity element, then we put A, then we put B, then we put C, then we put D, then we put A. So this is how we put in the Kelly table, and this is the definition of Kelly table. Like in the Kelly table what we do? We put all the elements like this. Okay, we put like all the elements like this. Similarly here also A, E, A, B, C, D, E. This is how we put all the elements in the Kelly table. Remember, when we put all the elements in the Kelly table like this, so all these elements are different, because this is how we put them. We put all the elements and we do not repeat the elements, so all these elements are different. If you have, for example, if you have 6 elements, then you will put them like this. Okay, if you have 3 elements, let's assume you have 3 elements 0, 1, 2, then you will put them like this. Okay, so in the Kelly table, these all in the header all these are different. Yes. Okay, so this is how we make the Kelly table. Now let's assume that in some row, duplicates are there. Let's assume that in this row duplicates are there. Means let's assume here we have X and here we have X. Let's assume here we have X, here we have X. Okay, we don't know what is X. X can be anything. Like from here X can be anything. Okay, so let's assume duplicate is there. Let's assume duplicate is there. Now if duplicate is there, then what is happening? See, B star C, you can see this is X, so B star C is equal to X. Similarly, B star D is equal to X. B star D is equal to X. Now this and this, so from this and this you can say B star C is equal to B star D. Okay. Now what you do? You just multiply both sides with B inverse. Just multiply both sides with B inverse. Then this will be B inverse into B. This is nothing but identity element. So identity element multiplied by C is equal to identity element multiplied by D. What is this? Identity element multiplied by C, that is equal to C, because when you multiply anything with identity element, then you will get the same thing. So this will be C, and this is identity element multiplied by D. So this will be, so you see we got a contradiction. What is contradiction? We got C equal to D, but we know C is not equal to D, because in the Kelly table, when we put the header, okay, in the header we do not repeat elements. All the elements are different. Okay, so this is the contradiction. You can see this is the contradiction. So if this is the contradiction, then of course we have done something wrong. Okay, because we have found some contradiction. Okay, we have found some contradiction, so we have done something wrong. What is that wrong thing that we have done? This is the wrong thing we have done, because we have allowed duplicates. So this is the wrong thing we have done. So that's why I am saying that if you have Kelly table for any group, then there will be no duplicates in any row, in any column. No duplicates will be there. Okay, so this is our behavior of Kelly table. Now this is Lagrange theorem. What is this Lagrange theorem? If G is a finite group, then if H is subgroup of G, then order of H will divide order of G. This is a very simple theorem, and we can solve question. Let's take this question. Let's assume G is a group. Let's assume G is a group such that order of G is equal to 3 to 3. Let's assume order of G is equal to 3 to 3. Okay. Now, so we can see, first of all, this is order of G. Order of G is equal to 3 to 3, and this 3 to 3 is actually nothing but 17 multiplied by 19. You can do the factorization. You can do just simple factorization. This is nothing but 17 multiplied by 19. Okay, so you can, if I ask you question, okay, can G have subgroup of size 18? This is my question. Can G have subgroup of size 18? So you can answer it very easily. No, there won't be any subgroup of size 18. Why? Because Lagrange theorem says that if you have subgroup of size 18, then that should divide 3 to 3. But you can see 18 does not divide 3 to 3. So that's why you can say that no subgroup of size 18 is possible. Okay. Now, what are the subgroups possible? So if your order of G is equal to 3 to 3, which is nothing but 17 multiplied by 19, then you can just check what subgroups are possible. The subgroup of size 1 is possible, because 1 divides 3 to 3. Okay, 17 will divide 3 to 3, because this 3 to 3 is equal to 17 multiplied by 19. So 19 will divide, and also 3 to 3 will divide. So these are the possible subgroups. Remember, these are the possible subgroups. So these are the possible subgroups. Okay, and remember, 18 is not possible subgroup, 20 is not possible subgroup, 23 is not possible subgroup. These sizes are not possible. So the only subgroups that are possible is this 1, 17, 19 and 3 to 3 itself. So these are the possible sizes for the subgroup. Okay, remember, this is trivial subgroup, this is also trivial subgroup. This we already know. This is trivial subgroup, this is trivial subgroup. So if I ask you what is the maximum size non-trivial subgroup, if I ask you what is the maximum size non-trivial subgroup, if I ask you this question, maximum size non-trivial subgroup, because I am asking non-trivial subgroup, So 3 to 3 you cannot consider, because 3 to 3 is this G is not a non-trivial subgroup. So you will have to answer 19. So the answer will be 19. So this is how you can apply this Lagrange theorem. Very easy. You can see this Lagrange theorem is very easy. You can very easily you can see. Okay, so you can solve questions. For example, let's take one more example. Let's assume order of group is 19. Okay, then my question is there any non-trivial subgroup? Is there any non-trivial subgroup? This is my question. So the group G, the order of group G is 19, and my question is there any non-trivial subgroup of G? You can try this question. Answer will be no, because see, this is a prime number. So the only numbers which divide 19 is 1, 19, and you know this 19 and 1, these are trivial subgroup. These are trivial subgroup. Remember, these are trivial subgroup. So there is no non-trivial subgroup. There is no non-trivial subgroup. The answer will be no. There is no non-trivial subgroup. Manish, Sakshi, is it clear? You can see there is no non-trivial subgroup, because this 19 is a prime number. So there the only number that can divide 19 is 1 or 19. Now this 1 is trivial group, and trivial group is trivial subgroup also, and this 19 is G itself, and G is trivial subgroup. So there is no non-trivial subgroup. So that's why this is how you can apply Lagrange theorem. So remember, this is a very important theorem. This Lagrange theorem is very important. Okay, now let's see the next concept, that is cyclic group. That is cyclic group. This is the next concept. We can see cyclic group. What is this cyclic group? This cyclic, before we see a cyclic group, let's see what is generator. Generator. What is generator? This is the first concept we must see. Okay, let's see. The first concept we should see is what is generator. Generator of a group. What is generator of a group? Generator of a group, let's assume your group is G. Let's assume this is your group G. Then element G of, basically this element G of this capital G is called generator. Is called generator if and only if you can generate every element. You can generate every element. Basically, for all elements in G, this A can be generated from this G by doing some power. So G power n is equal to A for some n. This is the definition of generator. Don't worry, I am going to take example and I am going to show you what is this like. Okay, so basically this is generator. Generator means something that generates. Okay, so if you have a group, then element of this group, this G, will be called generator if and only if every element can be generated from G. This every element can be generated from this small g, means small g power n is equal to A for every element. Let's take this example. Let's assume this is your group. In this group you can see one is generator. For this group you can see one is generator. This one is generator. Why? Because you can generate every element. Okay, for example, you can generate every element. How will you generate 0? Because you know 1 power 0 is equal to 0. This we have already seen. 1 power 0 is equal to identity element, and identity element is 0. So 1 power 0 is 0. 1 power 1 is 1. 1 power 2 is 2. 1 power 3 is 3. 1 power 4 is 4. So this is how you can generate all the non-negative numbers. Can you generate all the negative numbers? Yes. 1 power minus 1, this will be minus 1. 1 power minus 2, this will be minus 2. 1 power minus 3, this will be minus 3. 1 power minus 4, this will be minus 4, and so on. So you can see that every element is generated from 1. This one can generate every element. So that's why this is called generator. Okay, so this is the reason to call it generator, because this one can generate every element of this base set. This base set is set of integers, and every element can be generated. You can see 0, 1, 2, 3, these elements can be generated. -1, -2, -3, -4, these elements also can be generated. So this one is the generator. Okay, let me ask you next question. Let me ask you this question. So again the same thing, z comma plus, this is your g, and my question is 2 a generator? Is 2 a generator? So you can see this is not a generator. Why? Because from this 2 you cannot generate 1. For example, see, 2 power 0 will give you 0, 2 power 1 will give you 2, 2 power 2 will give you 4. So you can generate 0, 2, 4, these things you can generate. 2 power -1 will give you -2, 2 power -2 will give you -4, 2 power -3 will give you -6. So you can see one thing, that this 2 can generate all the even numbers. This 2 can generate all the even numbers, but this 2 cannot generate odd numbers. So that's why this 2 is not a generator. This 2 is not a generator. So the answer will be no, because 2 is not a generator, because 2 cannot generate all the elements. This 2 cannot generate odd numbers. This 2 cannot generate 1. This 2 cannot generate these things. Let's see next question. We have seen this group. Do you remember this group? In the beginning of the today's class, we have seen this group. This is nothing but Z4. Z4 is nothing but 0, 1, 2, 3. This is your and this is your modulo addition. This is your modulo addition. Modulo addition 4. Okay. For this group, let's call it group G. Tell me what are the generators for this group. What are the, remember, there can be more than one generator. Okay, there can be more than one generator, or there might be no generator also. Okay, so you need to find all the generators. If there is no generator, then you need to say that there is no generator. So for this question, let's see. You can try this question, let me answer it. For this question, let's see, is 0 generator? Is 0? Okay, let's check this. 0 generator? No. 0 is never a generator. Remember, identity element can never be a generator. Identity element can never be a generator. Why? Because 0 power 0 will be 0. 0 power 1 will be 0. 0 power 2 will be 0. 0 power 3 will be 0. 0 power -1 will be 0, and so on. So because identity element can generate only itself. Identity element can only generate itself. Identity element is a very selfish element. It will only generate itself. Remember, that's why identity element can never be a generator. This one, is this a generator? Yes, this is a generator. Why? Because 1 power 0 is nothing but 0. So you have generated 0. 1 power 1 is equal to 2. You can 1 power 1 is equal to 1. 1 power 2 is equal to 2. 1 power 3 is equal to 3. So you can generate everything, you can see. So this one is a generator. This one is a generator because you can generate every element. Let's see, is 2 a generator? Let's see this 2. 2 is a generator or not? Let's see. Let me ask you this question. 2 is a generator or not? So you can try this question. Let's see. See, 2 power 0 will be 0. Yes, 0 is generated. 2 power 1 will be 2. So 2 is generated. 2 power 2 will be, what will be 2 power 2? First of all, what will be 2 power 2? 2 power 2 will be nothing but 2 plus 2 mod 4. So this will be 0. Okay. What will be 2 power 3? That will be nothing but 2 power 3 will be nothing but actually 2 plus 2 plus 2 mod 4, that is equal to 2. So you can see what will be 2 power minus 1. 2 power minus 1 will be equal to, what will be 2 power minus 1? 2 power minus 1 will be equal to 2. So 2 power minus 2, what will be 2 power minus 2? That will be equal to 0, because 2 power minus 2, that will be equal to 0. So you can see one thing, this 2 can generate 0 and it can generate 2, but this 2 cannot generate 1 or 3. So this 2 is not a generator. This 2 is not a generator. Let me ask you next question. Is 3 generator? My next question is, this 3 is a generator or not? Let's check. This 3 is a generator or not? So you can try this. Let me answer it. 3 power 0 is 0. So 0 is generated. 3 power 1 is equal to 3. So 3 is generated. 3 power 2. What is 3 power 2? That is nothing but 3 plus 3 mod 4. What is 3 plus 3 mod 4? That is 2. So 2 is generated. 3 power 3. What is 3 power 3? That is nothing but 9 mod 4. That is nothing but 9 mod 4. And what is 9 mod 4? That is equal to 1. So 1 is generated. You can see this 3 is generating 0. This 3 is generating 3. This 3 is generating 2. This 3 is generating 1. So 3 is generating everything. So 3 is a generator. Okay, some students have directly said no. You should not directly say no. You should try, you should take copy, you should take pen, you should try to solve. Okay, don't directly say no. So this 3 is a generator, you can see. This 3 is a generator. You can check, this 1 is a generator, 3 is a generator. So for this group, we have 2 generator. Okay, so 3 is a generator, remember. Okay, for this group, we have, remember, we can have more than one. So we can have more than one generator also. Or we can have no generator also. For example, take this, take this example. I am going to give you another example. What example we can have? So what example I can give you in which we do not have any generator? In which we do not have any generator. What example I can? Let me think. If I so. Natural number and multiplication does not have a generator. Let's see this. Let's see this thing. Okay, so right now I can't remember such example, but I will give you on WhatsApp. I will send you an example in which there is no generator. Such examples also we have. So this is the concept of generator. Now what is a cyclic group? What is a cyclic group? What is a cyclic group? Cyclic group is a group in which we have generator. This is a very simple definition. So group G is cyclic group. This group G is cyclic group if and only if we have at least one generator. At least one generator. This is the definition of cyclic group. What is cyclic group? Cyclic group is a group. Cyclic group is a group in which we have at least one generator. Okay, so this is your this is your cyclic group. Okay, now so this is the definition of so you can see in all the examples that we have seen, those were cyclic group, but because there was at least one generator. So cyclic group is a group in which we have at least one generator. Okay, so such group are called cyclic group. Okay, so let's see some examples. You can take some homework questions. Okay, some homework questions I am giving you. You can try these questions at home. So the first question is, okay, don't solve right now. Okay, don't solve right now. These are for your homework. So the first is, you need to find whether the given algebraic structure is a group or not group. This is you need to check, group or not group, this is you need to check. Okay, so the first example is z comma plus, the second example is ze comma plus. What is ze? Z is set of even integers. Okay, the third example is zo comma plus. What is zo? Zo is set of odd integers. Remember, this is set of odd integers, set of odd integers. The next question is z under multiplication. The next question is multiples of 7 under addition. Multiples of 7, so I can say multiples of 7. Multiples of 7 and the operation is addition. These 5 questions you can check. You need to find group or not group, so you need to find this. Okay, so yeah, Khushbu is saying if A is a generator, then A inverse is also a generator. Yes, this is true. Why? See, if a power n is equal to some element, let's assume a power n is equal to, let's assume, some element x, then you can very easily find a inverse power minus n. You can find a inverse power minus n, that will be equal to x. So if a is generator, then a inverse is also generator. Okay, so if a is generator, then a inverse is also a generator. So this is how you can very easily prove it. Okay, Khushbu, is this clear? So now you this is homework question, these 7 questions. This is z comma plus, this is set of even integers, this is set of odd integers, and this is z comma multiplication, and this is, in this our base set is multiples of 7 and the operation is addition. Let me give you answers. This is a group, this is a group, this is not a group, this is not a group, and this is a group. So you can check all these. So I have just given you answers. You can check all the four properties and you can try to check. Now let's see the next concept, homomorphism. Homomorphism. Actually, what is this homomorphism concept? Let me tell you one thing. Actually, this is a very interesting concept. This homomorphism, isomorphism, these are very, very, very interesting concepts. And in the complete course, we will study these concepts in very detailed manner. I will give you intuition, like from where this homomorphism concept came, okay, why it was required, okay, all these things, okay, why it was discovered, okay, what is the purpose of this homomorphism, all these things we will see in the complete course. Okay, so in the complete course all these things will be discussed. Okay, many examples will be discussed. Okay, motivation will be discussed, purpose will be discussed. Okay, from where it came, the history, everything like this homomorphism is so interesting concept that we are going to discuss this concept in a very detailed manner in complete course. I told you in the last class of group theory also I told you that these concepts, homomorphism, isomorphism, ring, field, these concepts actually require some time. Okay, so we cannot actually cover these concepts in crash course if we want to cover them in a good manner. So what I will do today in crash course, I am only going to give you definition of homomorphism and 2 examples I am going to do, so that you can solve your questions in the NET exam. Okay, but remember, in the complete course all these things, homomorphism, isomorphism, and all these concepts, cyclic group, generator, this Language theorem, all these things we are going to study all these things. So we are going to study all these things in complete course in a very detailed manner. Here right now I am only going to give you the definition and example. Basically you will be able to solve all the questions. Okay, let's see this homomorphism. So you will be able to solve all the questions in your NET exam. Okay, after this definition, and we will see 2 examples. Let's see what is this homomorphism. Let's assume you have 2 group, G and H. Remember, these are 2 different group. Let's assume this is G comma star and this is H comma hash. They can be entirely 2 different groups. Like this is your group G1 and this is your group G2. So these 2 group you have. Let's assume these 2 group you have. Now homomorphism is nothing but a function. This homomorphism is actually nothing but a function f from G1 to G2. So this homomorphism is nothing but a function f from g1 to g2 such that if you have two elements from g1, if you have two elements, so basically actually this is a function, remember, this is your g1, this is your g2, so let's assume this is a, this is b, and so on. So because this is a function, so what it will do, it will map, so this will be your fa, this will be your fb, because this is a function. Now this function has a property. What is this property this function has? So if you have any two elements of this g1, then f of a star b will be equal to f of a hash f of b. This is the property. If this f has this property, then this f will be called homomorphism. Don't worry, this is just a definition. I am going to take examples and I am going to show you how to use this definition. Okay, don't worry about it right now. Okay, this is just a definition. Let's take example. Let's take example. So for example, what we can do, let's take this example. Yeah, so our group g1, I am having a group g1. Okay, focus on this example. I'm giving you a group g1, and what is that group g1? That is your 1 minus 1 iota minus iota. This is your group under multiplication. This we have already seen, this group. Okay, another group we can have is this. Another group we can have is this 0, 1 modulo 2. This group is nothing but your z2 modulo 2. If you remember, what is z2? Z2 is nothing but 0, 1, and this is modulo addition. This is modulo addition 2. So these two group you have. Now I am going to give you a function f from g1 to g2. I am going to give you a function. You only need to check whether this function is homomorphism or not. This is you need to check. Okay, so what is the function I am giving? So a function I am giving from g1 to g2, a function I am giving, and this function is like this. F of x is equal to, this function is like this, f of x, wait a second. Okay, so let's not take this example. Let's take another example. Actually, this example will be quite hard. So let's take an easy example, and then we will check that example. So the example we can take is this. Let's assume your g1 is a set of integers and modulo addition, and g2 is also set of integers and modulo addition. Okay, this is your group. So this is your g1 and this is your g2. Of course you can see g1 and g2 are same, but of course this is your group g1, this is your group g2. Now I am going to give you a function from g1 to g2. Okay, basically I am going to give you a function from z to z. From this base set to this base set, I am going to give you a function, and this function is like this. Fx is equal to 2x. You need to check, is this function homomorphism? My question is f homomorphism? So how to check this question? Very easily you can check this question. Just use the definition of homomorphism. See, the definition of homomorphism is this. Let me write it again. The definition of homomorphism is this. If you have homomorphism from a group g1 to g2, if this f satisfies this property, the f satisfies this property a star b. Remember, this g1 has the operation star and this g2 has the operation hash. These are two different groups. These could be same group, different group, anything. There could be any group. This is one group, this is another group. Now if I give you a function from g1 to g2, okay, such that f a star b is equal to, remember here we have a star, f a star b. Why we have a star here? Because this function is from g1 to g2 and the operation of g1 is star, so that's why f a star b is equal to f a hash f b. Remember why? Because this function is from g1 to g2 and the operation of g2 is hash. So if this property is satisfied, then we will say that f is homomorphism from G1 to G2. So let's check. This is our example. Let's check. In this example, let's check. In this example, they have given us a function. This is the function they have given. So basically, they have given a function from Z to Z. From Z to Z, they have given a function. And what is this function? This is nothing but fx equal to 2x. Let's check if this property is satisfied. What is the property? This is the property we must satisfy. Fx star y is equal to fx hash fy. This star is operation of G1 and this hash is operation of G2. Let's check. So f of, what is star? Star is plus, because operation of G1 is plus. So x plus y is equal to, let's fx. What is hash? Hash is operation of G2, that is plus, that is also plus. So fx plus y is equal to fx plus fy. What is this fx plus y? You can check. The fx is equal to 2x. So what will be fx plus y? This will be 2x plus y. This is equal to, what is fx? Fx is nothing but 2x. What is fy? Fy is nothing but 2y. So this is your 2x plus 2y is equal to 2x plus 2y. So this property is satisfied. Yes, this property is satisfied. Hence we can say that this function is homomorphism. Okay, this function is homomorphism. So this is how you can find whether a function is homomorphism or not. Okay, so let's take one more example. Okay, don't worry, let's take one more example and now you will understand it. Let's take G1. Let's take, this is our G1. What is G1? G1 is nothing but R under plus. This is our G1. This is our group G1. Basically R under plus. What is R? R is nothing but set of real number and the operation is plus. Okay, and what is G2? G2 is positive real number under multiplication. This is our G2. See, this is our G1, this is our G2. Okay, this is G1, this is G2. Now I am going to give you a function f. From G1 to G2, I am going to give you a function. Okay, basically from this base set to this base set, I am going to give you a function. Okay, what is this function? This function is like this. F of x is equal to e power x. This is my function. Remember, this is my function. So this is the function I am giving. Okay, we have G1, we have G2, we have two group. This group G1 we have, this group G2 we have. Now I am giving you a function f. This function f is from G1 to G2. And how I have defined this function? This is how I have defined. Fx is equal to e power x. Now you need to find, is this f homomorphism? Try this question. Just use the definition. The definition says that, the definition is like this. A star, fa star b is equal to fa hash fb. This is the definition. If this is satisfied, then f is homomorphism. Okay, remember, this star is the, if this f is from G1 to G2, then this star is operation of G1 and this hash is operation of G2. This is the only thing you need. This is the definition of homomorphism. Nothing, like, it's just a very fixed definition we have, very simple definition we have. We just need to check this simple definition. Okay, let's check it. So let's check whether this function is homomorphism or not. Let's try to check this. So f of a star b, we need to check if this f a star b is equal to f a hash fb or not. This we need to check. Okay, what is this star? This star is the operation of G1. The operation of G1 is plus. So f of a plus b is equal to f of a. What is this hash? This hash is operation of G2. Operation of G2 is multiplication. So fa multiplied by fb. What is fa plus b? From here you can find what is fa plus b. See, fx is equal to e power x. Fx is equal to e power x. So what will be fa plus b? This will be equal to e power a plus b is equal to, what is fa? Fa is e power a. What is fb? Fb is equal to e power b. Now this is nothing but e power a multiplied by e power b. You know this thing, e power a plus b, this is nothing but e power a multiplied by e power b, this is equal to e power a e power b. So yes, this property is satisfied. So yes, this property is satisfied, hence this function f is homomorphism. So anyone has any doubt in homomorphism? Very simple, let me tell you the procedure. You have a group G1 and the group G1 has this operation, and you have a group G2, this group G2 has this operation. Okay, if I give you a function from G1 to G2, if I give you a function from G1 to G2, then f is homomorphism, f is homomorphism if we satisfy this property. If we satisfy this property, what property we need to satisfy? Very simple, f of x star y is equal to f of x hash f of y. Remember, just need to take care of this thing. This star is operation of G1 and this hash is operation of G2. You just need to check this property. If this is satisfied, means if this is equal to this, if both sides are same, then you can say that this f is homomorphism. Okay, so I think it should be clear. Anyone has any doubt, then you can ask. So let me give you another example. Let's take another example. For your practice, we can take another example. G, your function, your group G is this, R plus under multiplication. This is your G, okay, and this is your group H. I am giving you two group H. H is nothing but R under addition. Okay, so now you have, this is your G, this is your H, and I am defining a function from G to H, and this function I am defining like this: f of x is equal to log x. Fx is equal to log x. This is my function. Tell me, is this function homomorphism? Is this function homomorphism? So focus here, let's see here. Very easily we can check. Okay, the very simple, like just we have a procedure. Okay, there is nothing. Okay, don't be scared of this homomorphism. Very simple procedure we have. So he has given us a function from G to H. He has given us a function, and fx is equal to log x. Let's check what we need to check. Just fixed thing we need to check. We need to check that fa star b is equal to fa hash fb. This we need to check. Let's check it. What is fa star b? Remember, this star is the operation of G and this hash is the operation of H. So what is a star b? That is nothing but a multiplied by b is equal to fa plus fb, because this hash is plus. Okay, so we need to check, is it true? What is fa multiplied by b? What is this? What is this? See, fx is equal to log x. So what is f? This will be equal to log a into b. Is now you know this thing. You know this thing that log ab is equal to nothing but log a plus log b, and this is what we wanted. We wanted that log ab, that this is equal to fa plus fb. Yes, log ab is equal to log a plus log b. This is the property of logarithm. So yes, this is a homomorphism. So f is a homomorphism. Very easily you can check. Okay, so is this clear? F is a homomorphism. Very easily we can check. Just a fixed definition we need to apply. So we have seen three examples. We have seen. If it is clear, then you can let me know. If it is clear, just write clear. And if it is not clear, then just re-watch this video, re-watch this lecture, and work out all these three problems again on your own. Okay, on your own, try to work out these problems and you will get it. This homomorphism is a very easy concept, you can see, and this is a very important concept also. Remember, in complete course I am going to spend around around 2 hours on this homomorphism. Okay, at least 2 hours I will spend on this homomorphism, 2 hours, okay, in the complete course, because this is a so interesting concept actually. Okay, so right now I have just given you definition, I have given you examples, so that you can solve all the previous NET questions. If they will ask you question in NET exam from homomorphism, then they are going to do, they are going to give you two group, and they are going to give you a function, and then they are going to ask whether this function is homomorphism or not. Very easily you can check. All you need to do is just apply this definition, apply this procedure. Okay, now let's see the next concept, that is isomorphism. Let's see this concept, isomorphism. If you have two group G1, G2, see, first of all, what is homomorphism? Let's see homomorphism. Okay, let's understand homomorphism. Homomorphism is like this. If you have a function from G1 to G2, this function is homomorphism. For example, let's assume this is G1. Let's assume this is G2. So this is your G1, this is your G2. Okay, so this is your G1, this is your G2. Okay, now what is homomorphism? Homomorphism is like this. You have element and you are basically mapping it like this. So you can map two different elements to the same element also. Remember, in homomorphism you can map two different elements to the same element also. Okay, similarly in homomorphism it may happen that some element of G has no image. So it's like this. Homomorphism, see, homomorphism is a function. Remember, homomorphism is a function, okay, is a function. Now homomorphism need not be one, and it need not be onto. So this one and onto, these requirements are not there. When we study homomorphism, then these requirements are not there. Okay, so now coming to isomorphism is a homomorphism which is bijection. So let me define isomorphism. Isomorphism is like this. Isomorphism is a homomorphism and bijection. Means F is isomorphism if and only if F is homomorphism and F is bijection. So this is how you can find isomorphism very easily. All you need to do, first you need to check homomorphism, then you need to check bijection. Bijection means one and onto. These two things you need to check. Okay, so we have already seen this example. We have already seen. See, this example we have seen. This example, our group G was R plus under multiplication, and our group H was R under addition. These two groups we had, and we defined a function from G to H. What was this function? This function was fx is equal to log x. We have solved this question already. You remember, this was our third example of homomorphism. So we have already solved this question. So this f is definitely a homomorphism. We have seen this thing. F is a homomorphism. This we have already seen. Now let's see whether this f is isomorphic or not, whether this f is basically bijection or not, because it is already homomorphism. Okay, homomorphism, this condition is already satisfied. Now let's check if this f is 1 and onto. Let's check. So what is this f? This f is from this base set to this base set. Basically this function f is from r plus 2 r, and this is our function. This is our function. First of all, let's check for 1. Let's check for 1. Yes, this is 1. Why this is 1? Because let's assume you have log x equal to log y. If you have log x equal to log y, then you know x is equal to y. So this is a 1 function. Remember, this is a 1 function. This logarithm is a 1 function. You know this thing, because if you have two different elements, then their images will be also be different. If you have x not equal to y, then log x will not be equal to log y. This 1 function onto function we have already studied in functions. Okay, this we have already covered in the functions. We have already covered this. So this is a 1 function. Okay, so this is a 1 1 function. Now let's check, is it a onto function? Yes, it is a onto function, and actually this logarithm, remember this thing, this logarithm function is actually onto. Why? Because if you see the graph of log function, then this is like this is the graph of log. So the range of log is actually real number. So the range of log is a real number. So that's why you can say range is equal to codomain. So this is a onto function also. Okay. So actually this logarithm function has this property that if you draw the diagram of log, if you draw the graph of log x, then the log x graph will go like this. So you can see this will go like this. Basically this will go like this. So you can see the range of log x, is equal to actually r. Okay, and our codomain is also r. So yes, range is equal to codomain. Hence we can say that this function fx is both 1 1 and onto. So we can say that this is bijection, this function f is bijection, and we have already seen that this function f is homomorphism. So we can say that this function is isomorphism. So this is how we can check isomorphism. So remember, if you want to check whether a function f is isomorphism, then what you need to check, f is homomorphism and f is bijection. These things you need to check very easily. Okay, so this you already know. We have already seen three examples. For how to check homomorphism, and this is very easy. Just you need to check whether f is a bijection or not. So basically you need to check f is a 1 1, f is onto. These two things you need to check. Okay, onto, you already know what is onto function. We have already covered onto function, 1 1 function. These things we have already covered in the function chapter. You can refer to the function chapter. There we have already covered 1 1 function and onto function. Okay, so this 1 1, what is the definition of 1 1 function? The definition of 1 1 function is like this: if you have two different elements, then their images should also be different. Okay, this is 1 1 function. And what is onto function? Onto function is like this: every element of codomain must have pre-image. Every element of codomain must have pre-image. So this is the definition of onto. Remember how to check 1 1. How to check 1 1. If you have a function f, then the procedure to check 1 1 is like this: assume fx is equal to fy. Then if fx is equal to fy, then x should also be equal to y. So this is how you can check 1 1. Okay, so this is the procedure to check 1 1. Remember, this is the procedure to check 1 1. If I give you a function f, then how can you check 1 1? Very easily you can check. All you need to do, just make fx equal to fy. Okay, and now from this you need to get x equal to y. Okay, so for example, let's assume your fx is equal to 2x. Let's assume this is your fx. All you need to do is just fx equal to fy. First you do this, fx equal to fy. So what is fx? Fx is 2x, fy is 2y. Then finally from here we got x equal to y. So this is how you need to check. Okay, this is how you need to check 1 1 function. Okay, so this is how you need to check 1 1 function. And how you need to check onto function? Onto function is like this: basically your range should be equal to codomain. This is how you need to check onto function, because in onto function every element must have pre-image. Basically every element must have pre-image. Every element y must have pre-image x such that y is equal to fx. Okay, so this should happen. For example, you see the log x function was onto function. Why? Because y is equal to log x. From here you can find x is equal to e power y. So you can see that every element y has a pre-image. What is that pre-image? That pre-image is e power y. So every element y has a pre-image. What is that pre-image? That pre-image is e power y. So we can say that this log function is onto function. Okay, so this is how you can check homomorphism, isomorphism. We have done 3 examples on homomorphism. All those 3 examples you can solve for isomorphism also, because in isomorphism the one extra thing that you need to check is bijection. Basically 1 1 and onto. These are the extra things you need to check. Okay, and I have told you how to check one, how to check on two. Okay, so actually these concepts are over, and some other concepts are still remaining. So let's do one thing. So the time is about 2 hours. So some other things are over because in the UGC NET actually the group theory syllabus is huge. Okay, so you can see this ring, field, quotient, and many things are there. So this is a huge syllabus. So you need to tell me. Okay, I will do one thing. I will check the previous year UGC NET questions of group theory, and in those questions, if they have asked any question from ring, field, product, quotient, if they have asked any question so far, then we will cover it in the solution session of group theory. So today what you can do, just try to solve all the previous year questions of NET exam of group theory, and we will have a session, solution session for previous year questions. Okay, in that solution session, if there is any additional concept that is required, I will discuss that additional concept in the solution session. Okay, because we as I told you, I have already taken a lot of time. Actually I have already taken some they asked some questions on fields. So yes, we will cover this field, ring, all these basically all the remaining concepts we will cover in the solution session. Okay, so one more thing I want to tell you. So in this crash course actually you can see because we have timing issues. Okay, we have limited time, so that's why I'm only taking 2-3 examples for each concept. I am taking only 2-3 examples, you can see. But in complete course, okay, in the complete course we will have enough time. Okay, in the complete course every concept we are going to study in a detailed manner. Every concept. Okay, ring, field, this ring, field, homomorphism, isomorphism, okay, cyclic group, Language theorem, okay, mathematical logic, relations, combinatorics, all these things, all these things, okay, poset theory, lattice theory, everything we will study in complete course in a very 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 detailed manner. Like after this in this complete course, once I complete this discrete mathematics, I will like most of you, for most of you, this discrete mathematics will become favorite subject. Okay, so anyway, due to timing issues, due to our timing limitations, I can't cover more things, because we already have combinatorics to cover, combinatorics and also probability. These things I need to cover. Then I need to cover TOC also. So that's why there is some timing limitation that we have in crash course. Okay, that's why it is called crash course, right? In crash course you cannot teach everything, so that is the reason. And we have seen like more frequent topics from, we basically have seen all those topics from which most of the questions have been asked. Okay, so okay, so this is our lecture, and see you in the next lecture. In next lecture we will study combinatorics, means counting. Okay, so yes, I will share the PDF today. I will share all the PDFs, all the remaining PDFs I will share today. Anyone has any other doubt? तो अगले लेक्चर में हम देखेंगे कॉम्बिनेटोरिक्स. कॉम्बिनेटोरिक्स मीन्स काउंटिंग, एंड आफ्टर कॉम्बिनेटोरिक्स वी विल स्टडी प्रोबेबिलिटी. सो वी हैव 3 more lectures we have: combinatorics, probability, and probability will take 2 lectures. Okay, this combinatorics will take 1 lecture and probability will take 2 lecture. So we have 3 lectures. With TOC compiler will yes, TOC and compiler I will teach. In the complete course I will teach TOC, compiler, discrete mathematics, DBMS, and if you like those subjects, if you give good feedback, then maybe I can take more subject also. So that will depend on your feedback. So provide your feedback. Whenever we ask for feedback, you must provide your feedback, so that we know like what you like, what you don't like, so that we can improve. Okay, So that is why this feedback is important. Okay, I will teach right now. This is the plan that I will teach 4 subjects: discrete mathematics, TOC, compiler design, and DBMS. These 4 subjects I will teach, but depending on your feedback, I can take more subjects also. Okay everyone, so see you in the next lecture for crash course में TOC compiler मैं पढ़ाऊँगा. ओके, आई विल टीच TOC एंड कंपाइलर इन द क्रैश कोर्स. DBMS मैं नहीं पढ़ाऊँगा क्रैश कोर्स में, DBMS कंप्लीट कोर्स में पढ़ाऊँगा मैं. ओके, तो कंप्लीट कोर्स जो है वो क्रैश कोर्स से बहुत ज़्यादा बेहतर होगा एक्चुअली, क्योंकि हमारे पास ज़्यादा टाइम होगा तो हम ज़्यादा एग्जांपल्स ले पाएंगे, ज़्यादा चीज़ें देख पाएंगे, सारे कॉन्सेप्ट्स कवर कर पाएंगे, बहुत कुछ, मतलब बहुत सारी चीज़ें होने वाली हैं क्रैश कोर्स में, क्योंकि हमारे पास में सफिशिएंट टाइम होगा. कंप्लीट कोर्स में, क्रैश कोर्स में थोड़ी सी टाइमिंग लिमिटेशन है, तो उसके कारण क्या है कि थोड़े एग्जांपल्स उतने नहीं ले पाते, हर कॉन्सेप्ट के ऊपर दो या तीन एग्जांपल ही ले पाते हैं. लेकिन कंप्लीट कोर्स के अंदर हर कॉन्सेप्ट के ऊपर 10-15 एग्जांपल. लाइक लेट मी टेल यू, इन द कंप्लीट कोर्स when we will study DFA, at that time I will take almost 50 examples. You can see that's a lot of example. So in the complete course, when we will study DOC, in DFA, in deterministic finite automata, in DFA NFA, I will take around 50 examples. So you can see why this complete course is going to be beneficial. Okay everyone, see you tomorrow. Thank you.